Welcome to the first lecture of EE305 Power Electronics. We are starting off with Module 1. Now, before starting, let's first look through the syllabus. So first, we'll be dealing with SCR, its structure, the static characteristics and switching characteristics of SCR. Then we'll move on to di by dt and dB by dt protection. Then we look into various turn-on methods of SCR, 2 transistor analogy, series and parallel connection of SCRs, structure and principle of operation of other switches such as power diode, triacs, GTO, power MOSFET and IGBT, and we end the module with their comparison. We'll start off with SCR. Now, SCR stands for Silicon Controlled Rectifier. Now, from the construction and operational point of view, a thyristor is a 4-layer, 3-terminal minority carrier semi-controlled device. Now, that itself requires some sort of explanation. So if you look at the diagram, you can see that this schematic diagram shows that the SCR has 4 layers. Okay, P, N, P, N. 4 layers, and in between each set of layers we have a junction. Therefore, we have 4 layer and 3 junctions J1, J2 and J3. Now here there are 3 terminals for an SCR, that is anode, cathode and a gate. Now when compared to a diode which has an anode and cathode, we have an additional terminal known as gate. Now if you look at the symbolic representation, it looks almost like a diode, but the only difference is the additional terminal. Now this is a semi-controlled device because we can control when to turn on the SCR, although we cannot control when to turn off. Basically a thyristor. Now we have to remember that thyristor is actually the name of the family which includes SCR, but SCR is so famous that the name thyristor has become synonymous with SCR. Okay. So when we say thyristor here, we mean SCR, although originally thyristor stands for family of devices which include SCR, diac, triac, etc. Now let's get back to this. Basically a thyristor consists of 4 layers. Alternate, you have to make sure that it is an alternate. So if there is a P layer or P type layer, then we have an N type followed by P type followed by N type. Okay. Now the anode as well as the gate terminal are considered to be positive terminals, while the cathode is the negative terminal. Now how do you identify which is anode, which is cathode, if we only show the schematic diagram without marking out the anode and cathode? So the way to identify is that the terminal that is connected to the outer P region. Okay, if you look at the diagram, you can see that from the outer part there is one P region and one N region. Now whatever be the terminal that is connected to the outer P region becomes the anode. The terminal that is connected to the outer N region becomes a cathode, and the terminal connected to the inner P region is called the gate. So since gate and anode is connected to P, which stands for positive, they are designated a positive value, and cathode is designated a negative value. Now an SCR can be turned on by a current signal but cannot be turned off without interrupting the main current. What it means is that if you take the SCR, even if you apply a positive potential at the anode and a negative potential at the cathode, the SCR may not turn on until a trigger is given to the gate terminal. Now by giving a current signal to the gate terminal, you can turn on the thyristor, but you cannot turn off a thyristor or an SCR by removing the gate pulse or by giving a negative pulse. An SCR can only be turned off by interrupting the main current that flows through the thyristor or the SCR. Now another feature of SCR is that it can block voltages in both directions. That is, even if it is in the positive direction, that is anode is positive with respect to cathode, or in the reverse direction where cathode is positive with respect to anode, in both conditions you can block voltage, but it can conduct current only in one direction. That is, from anode to cathode only the current will conduct. We cannot send current from cathode to anode. Now, for large current applications, thyristors need better cooling. Now, this is achieved to a great extent by mounting them onto heat sinks. So SCRs has a very large power applications, and larger the power applications, the more heat dissipation is required, more cooling is required, and if such a situation arises, you have to make sure that it is mounted on heat sinks. Now during conduction, it offers very low forward voltage drop, so it almost acts like a diode itself. During the forward conduction, it hardly offers any resistance to the flow of current. But when compared with a BJT, thyristors have longer switching times. It means that to turn on and turn off, it requires much more larger time when compared to BJT. Now you take this fact along with the fact that you cannot actually turn off the thyristor when you require, you can see that these features have eliminated thyristors in high frequency switching applications involving a DC input. That is, if you use for choppers or inverters, you never see a thyristor there because of these two conditions. One is that they take larger switching times, and moreover you cannot turn off as and when you require. It has to turn off on its own. But in power frequency AC applications, where the current naturally goes through zero, because you are applying a sinusoidal wave, it has a natural zero. Now as long as you are applying for an AC circuit, AC applications, thyristors remain popular due to some of the conditions. What are the conditions? They have very low conduction losses, and its reverse voltage blocking capability is there, and it has a very low control power requirement. Now what do you mean by control power requirement? That means that the amount of power that is required, to control the SCR is very low. Say an SCR can have a value of up to say 150 megawatt. It can handle power capacity of around 150 megawatt, and still that SCR can be controlled by as low as 10 watt power. So that is what is meant by very low control power requirement. In fact, in very high power, in excess of 50 megawatt, AC-DC, that is phase control converters, or AC-AC cycloconverters, thyristors still remain the device of choice. An SCR is so called. Why do you call SCR SCR? Because silicon is used for its construction. Moreover, its operation as a rectifier can be controlled. Now, like a diode, SCR is a unidirectional device. Means that it allows the current to flow in one direction only from anode to cathode. But unlike the diode, which allows the current to flow as long as the anode is positive with respect to the cathode, a thyristor blocks the current flow from anode to cathode until it is triggered into conduction by a proper gate signal between the gate and the cathode terminal. Now, as long as you don't apply a proper gate signal between the gate and the cathode terminal, the thyristor wouldn't allow the current to flow from anode to cathode. Now this feature is different from a diode where it automatically allows flow of current as long as the anode is positive with respect to cathode.